Hello everybody, we continue to talk about theory and practice in finite element analysis and about accuracy. So today we will talk about a mythical 2 elements per thickness. There are a rule which says that we need to have 2 elements as minimum, 2 elements per thickness for thin element. So if we take a look to this two body with these two meshes, this will be a very coarse and very bad mesh, insufficient, and this is very good mesh because they have 2 elements per thickness and ideal form and so on. So why did I say that this rule is mythical? Because many users who know this rule and who apply this rule for their construction doesn't understand from which behavior this rule came. And when they apply this rule to any construction they mesh, they do dumb work in reasons that they create very big and very complex task with a lot of elements and nodes, and nope, they not give any advantages with those big mesh. Okay, let's talk about size of mesh. As we talked previously, if we have some size of elements and we have size of elements which are less, we obtain bigger task. And if we create 3 different type of mesh, one automatic with 1 element per thickness and with big element size, second with the same size in any direction for elements with 1 element per thickness, and the same situation but with 2 element per thickness when we have 2 element per thickness and the same size in any direction for element, we obtain very big difference in size of our task. First will be the smallest, the second will be 5 times more in general, and the third will be 5 to 10 times more than the second. So if it's really necessary, it's okay, but does it really necessary? On previous video we showed this example with plate, and we say that yes, it's really necessary, and we say that if we have 1 element per thickness, we have problem, especially if these elements are linear tetra. If these elements are quadratic tetra, non-linear tetra, or second order tetra with mid-side nodes, it's not so big problem. But it's better if we have 2 elements, 2 quadratic elements per thickness. And we obtain something like that, and we see that more elements we have through thickness, the better distribution of stress we obtain, the better distribution of stiffness we also obtain. And this is our graph about deflection, about stiffness, and about errors in deflection. So we understand that 2 elements per thickness, it's very good because they provide very small error. And the problem is here. When we talk not about plate, when we talk about beam profile, and when we mesh it with a solid mesh, with a tetra mesh, for example, as we see here, we obtain three different meshes. This is the first mesh about which we talk. One element per thickness, but big element. This is second. One element per thickness and same size in all direction. And this is third. And you can see that the number of elements we produce are very, very huge and difference are very big. So does it really necessary to obtain? Let's return to ANSYS Workbench. So to mesh, this mesh has 1,800 of elements and 4,000 of nodes. This object has 26,000 of elements and 147,000 of nodes. So the number of nodes and number of elements between those two meshes have a very big difference. The number of elements one to another have 13 times. The number of nodes has 30 times, around 30 times. So if it's really necessary, it's okay. But if we take a look into total deformation, we can see that the difference present in a third sign after the point. It's 0.3% of difference in deflection. This deflection distribution look very close, and if we shut our mesh, we can't say which object have better mesh. If we switch to our stresses, we can see that the beam with tetrahedral mesh have worse result, and this is much more accurate with some hotspot stresses and so on. But in general, you can see that results look the same. So it means that this I-beam with 2,000 of elements and 4,000 of nodes generate result very close by accuracy, by quality of stress distribution and stiffness distribution and displacement distribution and the quantity to this very fine mesh with 26,000 of elements and 150,000 of nodes. So why we don't need to use this rule here? Let's return to our presentation and take a look here. If we have a plate, a general plate, simple plate, the rule is correct. But if we use a beam with profile, we need to understand that this stress distribution are not for this thickness. It's for wall beam, for wall height of this beam. So these elements, when we talk, it's element 1 per wall size of this I-beam. And when we create even those mesh, we create couple elements per height, and it's more than 2 because we have one element in place of tensile, maximum tensile stress, one element in place of maximum compressive strength, and couple elements here which separate this distribution in any manner. And if we return here and take a look to this one, we can calculate 1, 2, 3, 4, 5, 6, 7, 8. 8 elements per height. 8 elements per height. So, this rule, in some case, in some manner, automatically apply for this object. And we don't need to create mesh like this if we need a general stress distribution, if we need a general behavior. We need this mesh only if we need a local stress distribution in some place. So, why does this rule are present in our engineering life? You need to understand that when this rule appeared, computer was very big in size and very small in possibility, in power. And engineers who use finite element analysis software do a lot of things, do a lot of tasks to simplify their simulation. And they use beams, they use shells, and they use solid only in those places where they doesn't have any other possibility. And if they doesn't have any other possibility, and they have seen solid construction in some small place and all other, for example, it's a shell and beam, and in some place for submodeling, for super elements, for better stress distribution in some place, and they have solid geometry, they use this rule, the rule which says that you need minimum 2 elements per thickness for better describing of stiffness and stress distribution. But now many mechanical designers which use finite element software import geometry from mechanical designer, from CAD, with thousands of parts, and if they even suppress the geometry, they only delete bolts, nuts, and maybe holes for these bolts and nuts. But this I-beam, C-beam, O-beam, and so on came into our task as solid geometry, for which they create solid mesh. And that's very other situation. So for these I-beams, for all other beams, you don't need 2 elements per thickness. But we need to understand that sometimes, even for beam section, we need 2 elements and even more. It's for local stiffness and local stress behavior description. You need to understand that in most cases, if we have plate or beam, it deforms and it has natural plane or natural axis, and in any point we have tangential direction and normal direction. And in a simple way, we think that for beam, for shell, our section profile always normal to this neutral axis, neutral plane. But we know that if we have a very big object, very long, for example, and so on, sometimes, or we have very thick plates or other situation, we need to use the Timoshenko theory, which says that we need to use additional derivative for obtaining this angle, which shown as blue line. It means that our section are not normal, but has additional angle. In real life, when we talk about real geometry, we need to understand that it will look not as the blue one, but as the red one. They have very strange deformed shape, and even those shape will be not symmetrical here and here. And when we have those type of behavior, we need a fine mesh to describe distribution. And we need to understand that our profile, our section, not only deform in direction of normal or tangency or something like that. We need to understand that every point of our section deform in any different directions and can not be common with the beam behavior and so on. Especially if we have non-symmetrical profile. This C-beam is symmetrical with horizontal axis, but not symmetrical with vertical axis. And they can provide a lot of different type of deformation when our web and where our plates deform by themselves, as not in general, but locally deform, and it can cause very different ways. So in those cases, we need number of elements which will be enough to describe those form of deformation per web, per plate, and so on. So per size. This is example from SolidWorks simulation course, and this is our solid geometry created in different way, and plate geometry also created in different way. And we can see that our shell plate geometry deformed the same, with the same character, with the same type and with the same values with any mesh if we use a plate element with mid-size. But if we talk about solid mesh, we can see that we need at least 5 elements per this plate to describe good behavior. And more elements we have, more accurate result we obtain. Because here we have difference about 10%, and here we have the same result. But here we have the difference 3 times. 3 times. So, from what type of understanding we can get this? If we take a look to this arc, it can be thin arc, it can be arc from circle. It can be part of parabola. And we can see that it's a deformation of our beam plate when it's fixed here with displacement and forced here. Or we can take a look only on this part and say that we have full fixation here on the middle and force on this end or this end. Or for example, it can be number of steps for time integration when we need to obtain good result for oscillation, and we need to understand how many elements or how many steps we need. We can see that one element or one step per this arc are not adequate at all. We can see that two elements, especially linear or two-step, create a very big error from the real geometry. We can see that 4 elements per this arc or 2 elements per half creates some difference, some big difference, but it's better than only one this line. And if we have 4 or 5 division per half, so 8 or 10 division per whole arc, we obtain a result which are very close to the real one, especially if we talk about the element and this element have mid sides. So the most important things that we need to understand is that if we need a global stress distribution and global stiffness distribution, and we have plate, the simple plate, yep, this plate better to have 2 elements per thickness, but sometimes it's enough to have 1 element per thickness and good stress distribution through all other direction. If we have the beam which meshed with solid element, we does not need to have 2 elements per any panel, per any web, and so on, per thickness of this web and panel. It's enough to have 1 element. But if we need a local stress distribution, we need to obtain mesh which will have the good stress distribution and good stiffness distribution for locally deformed object to describe those type of deformation. And we need to understand that it's better to use not solid mesh, but beam mesh or shell plate mesh, because it can create situation when you create smaller task and faster obtain solution. Here you can find a video about different type of simplification of your construction. Thanks, write a comments and questions below the video. Bye.